Thank you, Jacques, and thank you for coming so early, ladies and gentlemen. I'm happy to be able to give you a status report on what we call the LENRIA Experiment and Analysis Program, or LEAP. So we're taking the LEAP. We're not sure where we're going to land yet, but we'll see. So the goal of the program is to provide a means for LENR to break out, become a recognized and funded legitimate field of science. So the field needs three things. Ultimately, maybe on a 20-year time scale, commercialization. On a midterm time scale, scientific understanding. We're dealing with hopefully a very much shorter time scale, maybe a year or so, where the field will become widely recognized not only in the United States, but much more as a legitimate field of scientific research. Now, the hallmark of this program is to do very thorough work and very thorough documentation. Those of you who have been in the field know that there have been many experiments over the years that haven't been as thorough as they should be. And then in some cases, even though there were thorough experiments, the documentation left a lot to be desired. So we're trying to be very careful on both sides of that. The work is funded by the Anthropic Institute, Carl Page and Frank Ling. Frank, are you in the room? Maybe you're here? Oh, okay. So appreciate their support. On a personal note, I worked in this field almost 30 years before I had funding to do calorimetry. And once I started to do calorimetry, it was a jolt, to put it mildly. Now let's see if this works. Ah, good. So the possibilities for breakout are listed here. And by breakout, we mean awareness and acceptance of the field by the scientific community with adequate funding and so forth, something that we all hope for. And the possibilities are listing here: clear and accepted theoretical explanation, strong demonstration widely viewed, strong public backing by a very rich person, a replication of the 1985 meltdown by Fleischmann and Pons. Some of you know about that. I can talk with you about that more if you like. I can't go into detail now. If you can go to the store and buy one, probably the field will be accepted, okay? Or we can have a multi-lab replication experiment on a time scale of a year or two, and that we have control over. That's the only possibility of these several that we have the control over. So that's what we're doing. So an outline of the presentation, I'll give you some background on the program, and then talk about the materials and the experimental setup and the data analysis we're doing, and wind up with a single slide on the status. So this is a program that was conceived by Steve Katinsky, sitting there, and since he had the idea now already 6 years ago, we've looked at various options, and in 2016 decided to concentrate on the palladium boron alloy system, which has had some significant success, which I'll be talking to. So before the funding by the Anthropocene Institute, we had been getting ready for it, but with the current funding, we'll be able to complete the first phase of the program, and I'll show you what those phases are in a moment. So the situation is there's sufficient published data on LENR to show a number of things. It's a real physical phenomenon, as major promise as a new source of clean energy, but we're being ignored. Okay, so I tell people we're suffering ignorance. Okay, ignorance and ignorance, both. Okay, so the challenge is to get the attention of the broader community for both the understanding, the scientific understanding, and the commercial exploitation. So our strategy is to perform the same experiment, which has been qualified to produce excess heat at multiple major laboratories, produce reports on the conduct and the results of those experiments by each laboratory, and then coordinate simultaneous publication. So again, the goal is to change perception. We're looking for what Steve calls a tipping point. So this is a layout of the program. The first phase is to rerun the early experiments, update them, and let's see, I'm having trouble reading that. Modernize the devices and the measurements and so forth. And if that works, we'll have a very strong document that we can take to some funding source and say, please give us enough money to clone this a half a dozen times. Literally, clone the system. Hardware, software, materials, protocols, everything. And then we will go to some major laboratories, think CERN, and big laboratories in Japan and other places, in order to have them simultaneously run on our protocol, our materials, with our equipment and our software. And hopefully out of that will come a set of papers, a set of reports that can be reviewed and published simultaneously. So we would hope that we could publish in a really major journal, and the pioneering work by Google in breaking into nature recently, of course, makes nature a potential target for what we'd like to do. So the program involves the use of the original successful palladium-boron alloys plus newly made palladium-boron alloys, LabVIEW and other modern means of acquiring data, controlling experiments, acquiring data, improvement in experimental setup, especially the calorimeter, and then, as I said, the detailed documentation. Why palladium-boron? Well, Imam, who is here somewhere, where are you? There he is. In the mid-90s, made palladium-boron alloys at the NRL that worked 9 times out of 10 times in the hands of Mel Miles in different calorimeters in the US and in Japan. Early appearance of excess heat, oxygen-free palladium was produced. I could go into details there, but I won't do that at the moment. Be happy to talk with you more about it. So we think we have a candidate for what some people are calling a lab rat. And this is data that was taken using these alloys, taken by Mel Miles, reduced by Martin Fleischmann. This is 60 days, and this is a 0.17 watt excess, a third of a watt excess. So it's not large excess powers, but in most of these experiments, the signal and the noise was adequate to show that there really was something there. And if you look at this data, you see there's very little control, like many experiments in the field. It's all over the place. And the data points are infrequent, okay? So 60 days, only a few data points. So one of the things we wanted to do was to improve the data acquisition rate. This is a photograph of an ingot of the original material that we recently had swaged into 3 millimeter rod, a 3 millimeter rod, a meter long, by this company in Virginia. So we now have a substantial amount of the original material. We had a company make another ingot of the material, which is shown here, and it was swaged into a 3 millimeter diameter rod, about a third of a meter long. So we have a substantial amount of both the old, the historic, and the new materials. So we're doing analysis naturally of the composition and the structure of the materials. This is X-ray diffraction data taken by Kadri at the Naval Research Lab from the original material, and then from a small piece of the new material. And this is noisy because it was a small piece. So anyway, we have the data and are in the process of analyzing the structural data for this material. We're also performing electron backscatter diffraction to get the orientation of the grains on the surface. And we were really surprised when we saw this because of the large difference in the grain size between the legacy material, the old material, and the new material. So we have major differences. Now, that we view as a problem. We would like to have the new material just like the old material, but we're not there yet. But we are able to characterize the structure, and I won't show it, but also the composition of the materials in both cases. So the overall experimental flow is normal. We have the LabVIEW and the computer that controls the power supply, that controls the experiment, and the data comes in. And we have the challenge, the usual challenge of turning the power, that is computing power time curves, that is thermal power out versus time, from the measured temperature versus time data that we take from the inside of the calorimeter. This is the front panel of the LabVIEW with the control side on the left, the data capture side on the right. I don't think I have to go into detail here. We have several tabs that give us very detailed information as the experiment proceeds and then after the experiment for analysis. I don't want to spend a lot of time on this and the next couple of slides either because there are a lot of details. We are very, very interested in switching versus linear power supplies, okay, and in the noise of the power supply. So we have both kinds, and we're measuring the noise. Some people would say the noise is beneficial. It jolts the experiment. It increases the chance of producing excess heat. And other people say, no, 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 no. You want a very quiet power supplies. So we're seeking to run that question to ground. The temperature measurement setup is shown here. It's a 4-channel commercial system with milli-degree resolution and about a 100th of a degree accuracy, supposedly. We've checked it in an ice bath, so it looks not quite that good, but good enough for the experiment. The water bath, we have a temperature controller. It's nominally good to about 5 millidegrees, but it actually doesn't work that well. But again, it should be good enough. So this is a photograph of the setup from a few weeks ago when we only had one calorimeter in place. The calorimeter is shown here. These are the temperature measurement probes, the thermal controller here. It's been very, very useful to put this plastic cover over, both to reduce evaporation and also to improve the temperature stability. Okay, we could insulate it if we have to. The old calorimeter used by Mel Miles is shown here. It's the Pyrex test tube, and then oil, then copper, then insulation, then copper. It's too complex. I couldn't see through it, so we built a transparent calorimeter that has only 3 components: the lucite thermal barrier, a thin 800 micron layer of oil, and then the test tube in the middle. And that's working quite nicely. Here's a cross-section of it. Use mineral oil as the coupling medium between the test tube and the thermal barrier. We have a 3D printed structure in the bottom here to keep the test tube centered. It's worked out quite well. Okay, sorry. So this is a photograph of the cathode and anode in Mel Miles setup. He had a problem keeping it centered, so we 3D printed a cage here that there's good news and there's bad news. It keeps it in place, but the plastic gets soft, and it introduces other chemicals into the situation. So during this trip, our shop is making a Teflon spider like this that will go over the top and the bottom of the cathode to keep it centered in the test tube. The coils are well behaved. We have no problem with that. So we think we have the geometry in hand now. We wanted to know about the thermal behavior, so we put the calorimeter out on a table, put a resistor in to heat it, visible photograph on the left here, and then these are, as you see, infrared pictures. And the bottom line here is the imaging shows that the heat flow is primarily radial. There's not a tremendous amount of heat that escapes out the ends, which is good, of course, from a data analysis viewpoint. This is a plot of some of the calibration data, time here, temperature here. This was a platinum cathode in a deuterium electrolyte as close as possible. So when we would put in 1 watt of electrolysis power and then turn it off, 4 watts, turn it off, 7 watts, and so forth. And this is the bath temperature here. This is the temperature in the air above the water underneath the plastic cover, and this is the room temperature. We still have a problem with room temperature control, but we're about to fix that. Now, the thing that jumps out here is that as you go to higher powers, there's a slope. The calibration never equilibrates, where the input electrolysis heat balances the escaping thermal conduction, okay, the heat that escapes by thermal conduction. And as an aside, we put in an aluminum reflector around the calorimeter and found that the radiation does not play a big role in the transport here. So the calibration curve that we get, shown here, watts of input electrolysis power versus the temperature increase inside the cell, is not yet satisfactory because we have this uncertainty at the higher power levels. And it's almost certainly due to the changing electrolyte level at the higher power levels because we burn through the D2O faster, but we are verifying that in a run that's going on right now, and if necessary, we have a means of making an additional feed of the D2O in order to stabilize the electrolyte level. So that's a coming attraction, if you will. Now, the data analysis, as I say, going from the temperature time curves to the thermal power time curves is something that, if you dig into it, is very complex. Martin Fleischmann, Mel Miles individually and together wrote many, many papers on this. But we're trying to start from a very, I would call, simple level, where the increase in energy in a given time element is the difference between what you put in by electrolysis and what you lose by thermal conductivity. Okay, this is not, as they say, rocket science. It's relatively simple, but there are 2 kinds of problems. One is the problems with each one of these terms, plus there are missing terms, like the work done by the bubbles against the atmosphere. Okay, we don't have that yet. It's said by Mel Miles, from his experience, to be insignificant at low powers, but we're going to check that out. as an example of the problem here, so this is the mass inside the calorimeter, the specific heat and the rate of change of the temperature. So what do you count as inside the calorimeter? Is it only the contents of the test tube? Does it also include the glass? Does it also include the thin film of oil? Okay, John Paul's going like this. It's an issue here that is going to be exhaustively studied as we go forward, okay? So the data analysis, Miles took data every few hours. We're taking data every second. We smooth the data. We use the Savitsky-Galois algorithm to fit it, and then we can get rather good curves of the dt that goes into the first term of the data analysis. Okay, one of the things, I'm in an electrical engineering department, as is Peter, so noise is of great interest to us, okay, because that ultimately sets the limit of performance of an instrument like a calorimeter. So here's the photograph on the left of our setup, and we added a resistor there, so then we can put relatively small amounts of energy, not small compared to what we want to measure, but small nevertheless, a quarter of a milliwatt in, and see it on top of 4 watts of electrolysis power or with no power. So, you know, I'm bent on making sure that we understand what sets the minimum detectable limit of the thermal power in this experiment, the combination of measurements and the data analysis, okay? So that's absolutely going to be done. So to finish up, the status currently is the palladium boron materials, old and new alloys are in hand. As I said, the analysis of the composition and the structure, they're in progress. A sophisticated LabVIEW program exists and is being enhanced, and it'll be possible to program multiple runs. We now have 2 calorimeters in place, and we have the software in hand to run both calorimeters simultaneously. The hardware side, the power supplies, temperature monitors are in place. Temperature control in the laboratory is still an issue, but we're basically going to tell the university shut down everything. We'll buy a room unit, and we'll have the kind of control of the atmosphere in the room that we need. Many calibration runs have been made already as a function of various conditions, and we're looking, as I said, at the variation of the electrolyte level even as we speak. We have the basics of the thermal power determinations in place. Additional factors and noise limits will be determined, and we just started running with the actual palladium boron cathodes last month. Okay, so thank you for your attention. I'd be happy to answer any questions. Lynn.
Yes, if you could go back to the slide where you had it was the colorful slide with the various, I think you did an electro analysis of the lead.
Materials?
Yeah, of the materials. And I was wondering if you can identify, what are the various colors? What's the green, what's the purple, what's the blue, et cetera?
Thank you. Those are different grain orientations. So
Okay.
100, 110, 111, okay. So I apologize for not saying that, but yeah, that gives you information on the grains. And as many of you may know, Vittorio Violanti and his team found when they did materials analysis on this scale and then ran materials that when they had 100 faces on the surface, they were more likely to get excess heat than if they had 110 or 111 faces. Okay, so that's why we're interested in the what's called the texture from a metallurgical viewpoint.
The difference in texture may be due to the fact that you rolled or your ingot before
Yes.
annealing it again.
Yeah,
and
so
when you make a rolling and annealing, you get such a new structure.
Yeah. So if we cook the material at 650 C for 2 hours, Imam determined many years ago that you will anneal out dislocations and soften the material. If you go to 800 C for 2 hours, then you get grain growth. So we could anneal, vacuum, or anneal in a argon atmosphere the material, the new material on the right, to achieve something like that. So we have some considerable knowledge of what to do in that regard. But right out of the box, this is what we found with the materials.
And mechanical working before annealing is important. Okay.
Hello, my name is Slobodan from Swiss Oxy Hydrogen. I just want to make a small comment. I was working with the electrolyzers for a long time. One of the elements what should be took account in is the bubbles. You were talking about bubbles. If you have a lot of bubbles on the electro wire, it changed the resistivity. So you have to get rid of it to put, water pump or something that to remove all the bubbles from the wires.
Yeah, I appreciate that comment. We have measured for galvanostatic conditions the variation in the voltage due to bubbles, or more, if you apply a voltage, if you have a bubble on the surface, there's a dip in the current. Okay, so we have seen that in some nickel hydrogen runs. It's been analyzed by a colleague of mine in Switzerland, and we know that, but I don't know a way to stop it. So I'm going to be wanting to talk to you in detail about how to do that, because clearly the bubbles are good news and bad news. The good news is they stir the electrolyte, they lead to isothermal conditions inside the test tube, but they do block the cathode. So thank you.
Yes, my question is, how many watts do you need to get to boiling?
How many watts do we need to get to boiling? We don't know. We haven't run it to boiling yet, but we've run it to 85C with about 16 watts.
Yeah, because it carries 2 cells, they need 10 watts to get to boiling. Because the less watts you put, the better precision you get in the final results, obviously,
Yes, and when you look at calorimeters across the field here, this is not a high-performing calorimeter. It will be adequate for what we need.
Okay.
But if you say the Icarus calorimeters could boil at 10 watts, and I'm saying that we only got to 85C, with almost twice that, then it's a measure of the difference between those two calorimeters. Yeah, thank you.
Did you analyze with high precision, for example, like with ICP-MS both materials to see if there are some composition variation?
Yeah, we have gotten glow discharge mass spectroscopy done already, and I didn't present the data for reasons of time, and it's difficult to get a grasp of it in a short time. But we have that data, and we're going to do considerably much more chemical analysis on these materials, so we don't understand. Okay. Yeah, thank you.
Could such palladium-boron alloys be provided to other laboratories?
Our hope is that we will get excess heat. That is, we will verify in the current phase 1 program what Mel Miles has seen, and at that point, provide everything to 6 major laboratories, materials included, everything. So some of you may be sitting there, gee whiz, if this succeeds, I'd like one of these systems. Well, we will have a deal for you. We will provide you, as I said, the equipment, the software, the materials, the data analysis on a contract basis. You run our protocol on our time scale, okay? We'll have a contract with you. So we are hoping that we will see excess heat. We'll have a defendable basis for getting additional funding to clone the setup and then to interact with several major laboratories. Thank you.
Cool, thank you very much.
Okay, thank you.